Hey guys, so today we're going to continue on with our PCode series, and we're going to be talking about how execution is transferred into Windows API or normal standard CDLLs from the PCode string. So here we go. We have a very simple program in our form load. We just have a couple debug breaks and then I sleep. So before we get into the actual PCode part, I went ahead and compiled it as a standard executable, and I included debug symbol generation. So we can see what that looks like over here. Everything's been named for us. So we're at the top of our form load, and this one actually lacks the sleep call, but we don't need to worry about that. So we have, so all of the calls that happen in our form load, we can see highlighted here. And I've already renamed this one the call API. So what we're interested in is this call API stub. So it's not calling the API directly on its own, right from the procedure that it's invoked in. It always goes through this kind of stub, right? And so first we have an address. This is an API pointer, essentially. And if it's not filled out, so it loads the API pointer into EAX. If the EAX, it tests to see if it's 0 or not. If it is 0, then it goes into this load API section where it loads an import structure. And a structure has basically two long values, two offsets. The first is the DLL name, and then the second is the actual API name to look up. And then it will go into this VB runtime export, which is the DLL function call. Using that structure as the argument, it'll look it up, it'll resolve it. If it can't resolve it, the runtime itself throws an error, and then it will just jump to the address that's returned. So it basically resolves it, returns the result in EAX, or throws an error, and then it will jump to the EAX. And then execution will return back from where this had been called from. And if the API pointer has been filled out, then it will just jump to it automatically. So it caches the result in this address right here. So that gives us a little bit of basis of what a standard executable does. And now we want to know what the PCode executable does. So we've compiled this in PCode, and we've already disassembled it. And we can see we have two debug break calls. We have a get last error after each one. And then the second API call, we'd see has an argument. That's why I included sleep in here. Because just to highlight a slight difference as we go. So the API are called through this imp add call FPR for, that's probably R4 refers to like a 4-byte thing, a real 4 usually. Implicit add call, I don't really know. Haven't deciphered all the names yet. So let's see, what is the best place to go? So so here's our IDA thing. The debug break is going to break us into when we hit a breakpoint. So, or actually, I've already set a breakpoint on, so we have this imp add call FPR4. ESI again is pointing to our section of the byte stream. So I'll hit F7. ECX is now 0, and we can see that in our bytecode stream here. So our first 2 bytes are 0, and I'll show you what that is in a second. And then it's going to load the next 2 bytes into EDI. And again, EDI, that again is 0. The next 2 bytes were 0. It's going to jump past. ESI again is our pointer into our bytecode stream. So it's going to jump past those 4 arguments. The EDI value, the second 2 bytes that it grabbed out of the argument bytecode stream, it's going to add ESP to that. So EDI, all right, so it basically just cloned because it was 0. Now this EBP minus 54H is actually kind of if I go, I'm going to start debugging this. So the EBP minus vb6 is v6 uses the lower section of the stack as kind of housekeeping area where it stores some stuff, like the -14 is the current function start. We have some exception handler stuff. You know, you have to figure out each of these as you see them used and then figure out what they relate to. So this EBP -54 is the constant pool. And so the constant pool is something we haven't talked about yet. So if we go to the constant pool viewer, here is the pool for this entire form. The same pool's used for each like form module or class object. And we can see that we have 2 entries into the pool. And the first one is an external API reference for this debug break. And I've gone through and the tool automatically figures out what each pool entry is based on where it's pointing and stuff like that. It's kind of brute forces it based on all of these different types of things. And then it's showing the actual data here. So if we were to go to this address, and here I have it. This is the PCode version of the executable already disassembled. And if I go to that address, oh, we're already there. So let's see if I can, there. And this is going to look pretty familiar from what I had just shown you moments ago. You know, the DLL function call, this would be the, it's not displayed properly, but Ida wasn't able to make sense of it. But here you can see the API, and here you can see the, you know, so you can see that we're looking at the structure, and I could probably right here, come on, there we go. So there's our structure that it's being passed in. So the same thing, this still exists. This little stub still exists in our compiled executable. So well, we'll go back to this. So we're looking at our pool address into EDX. And then, so there's our pool ECX, again, our first 2 bytes, which is the index into the pool, times, you know, every one is 4 bytes long. So what it does is it's just looked up that address that I just showed you in the other IDA window. It's checking to see if it's 0, and then we fall through to, you know, another little stub of assembler here, you know, our events enabled. And then it's going to call into the API for us. So it's already retrieved the address, not of actual API, but of that stub backend, because we're looking at the runtime right now. We are in the runtime code that's handling the PCode. So now we're into the project1.exe. This is our cached pointer, and this is the first time it's been run, so that does not, it's not loaded yet. And so it's not loaded. It's going to go to that. Here's our structure. Here is the DLL function call address, export from the runtime, and then it's going to call it. I don't want to go into that. I'm going to step over it, and now we can see EAX has been loaded, and we have an address here. So this is going to jump us into kernel 32, debug break. Yes, and all right, so now we're back. So here, this was our call EAX, that we're back into our runtime, the .engine section, the vb6 runtime. And this is the call that happened, and now we're back into the next block of assembler that comes after that. And here we're checking our ESP and our EDI. And you can remember that EDI was a saved version of ESP plus whatever that second section of opcode was, these last 2 bytes. So basically the first 2 bytes are going to be the pool entry, and the second 2 bytes are going to be kind of the argument count, how many bytes the stack was modified by due to the function call. And debug break doesn't take any arguments, and that's why I added the sleep, is because, you know, here we have 4, and we pushed an integer, the argument for sleep, the sleep timeout. So you can kind of see those two things in action. So we're loading. It's going to check the stack. So it's checking these two values to see if the stack is still correct. If it's not, then it's going to throw stack error. So that passed okay. Now we're going to go and zero out EAX. Remember, ESI points to our next bytecode stream. So if I were to go down here and go to the ESI, the next thing is F5. And if we look down here, it should be, is it actually, oh, sorry, I had the wrong thing highlighted. It's 3C. And that indeed is our next opcode. That's what comes after it's actually this one. 3C is our next opcode for our get last error. And so that opcode at that address is going to be loaded into AL 3C. We're going to increment our opcode pointer to the next section because we've already consumed the actual opcode, and then you've already seen how we transfer execution to our next opcode in the previous video. So that gives you a little bit of an idea of how both PCode and native code in Visual Basic 6 transfers execution to Windows API and how that execution returns back. Now this is going to get a little bit more interesting once we go into callback functions. So we have, we're doing this part, we're transferring execution out to the C code, and then sometimes the C code is going to call back into our Visual Basic 6. But if the Visual Basic 6 is PCode, how does the runtime, or really the compiler, handle that? How does it set it up to enter the bytecode stream again? So that is all we needed to cover in this video, and we'll do callbacks in the next. Thanks.